So, perhaps the biggest thing that separates a lot of social simulators is not anything to do with methodology or subject matter, but whether you're an optimist or a pessimist, okay, about simulation. Whether you think, aha, we're going to do it very soon, and all these models, we're going to sort out all these problems, or you think, it's really, really difficult, and the more you get into it, the more difficult it seems. Okay, so I'm on the pessimistic wing of social simulation, as you probably gather. Okay, so this is the outline of the talk. So I'm going to go into some reasons why it might be impossible, or at least very, very difficult to do social simulation, and why it may appear possible even when it's not, how we can fool ourselves. Then I go a bit about into the modeling relationships, looking at the relationship between our models and what we're trying to observe, and try and relate all of this to some different simulation goals at a quite high level, and then try and talk about them with some example simulations, and I hope we'll have a lot of time for questions and you can argue with me, which I like. Okay? Edmund will be following with more specific stuff about choosing research questions and stuff like that, so it'll follow at least onto his talk, because I've talked to him and I know that's the case. Okay. So, we're starting with the pessimistic view. Okay, so whoops, what's happened?
There it is.
Okay, here we go. What's happened? Okay, so, I didn't know it'd be so difficult. Right, so 5 different reasons why it might not be possible to do social simulation. Okay, the first one is very fundamental. Okay, we are trying to model something that is fuzzy and semantic. People are doing meaningful actions with respect to each other. They're talking to each other in meaningful language, and we're trying to model it in this stuff which doesn't include meaning, which is a computer program, which is syntactic, which follows rules. Okay, so fundamentally trying to model something with a very different kind of thing. So we're not trying to do a model aircraft in the same materials as aircraft are made out of. We're trying to make a model, a model aircraft out of jelly, roughly. Okay. Now, you may say, okay, that's all right, but in lots of other areas they do the same. So in physics, they model physical stuff with numbers, and those are very different. So surely that's not a good reason why we can't do it. And in particular, that gap is bridged by what they call measurement in physics. Now, firstly, this took a very long time to develop, measurement techniques which actually relate these formal mathematical models, or simulation models now in physics, to what they were observing out in the real world. Okay, so if you're looking at the difficulties that Copernicus and Tycho Brahe and people like that, trying to relate their measurements of where these planets were towards these various theories of where they should be, it wasn't easy. It took a long time to develop these techniques. And maybe social sciences, the human sciences, haven't developed so many measurement techniques in the same way as physics, or they need to do a lot more before we'll be able to really bridge this gap between our models and what we are observing. In physics, there are some special reasons why numbers work, okay, because some things are really random at a fundamental level. They average out, and we're only observing them at the average level in a way that isn't true of people. Okay? So, for example, if you look at the volatility in a stock market, if the people were acting at all randomly, the bigger the stock market you would have, then the randomness would decrease as a proportion of the whole stock market, because randomness cancels out the law of large numbers. But it doesn't, of course. We all know that. The bigger the stock market, the more volatility you get. Okay? So people, at least in some circumstances, don't act like atoms. The randomness doesn't average out. Okay? You cannot rely on that effect for making numbers work. And one thing I always look for when I'm reading a paper is where people added randomness probability into their models. Have they thought about that? Have just stuck, oh, that's probabilistic, we'll stick this probabilistic. Now, you can't avoid that some of the time, but some of the time it's just done without thought. Okay? So even in physics, they're very aware of the limitations of analytical representation. So in physics, there's this whole culture of you have analytical representations, but then layers of approximations, different data models that come underneath that. If you actually look at what physicists actually do, it's not the simplified picture you will get from textbooks of this relationship between this model and what they measure. There's actually a lot of implicit steps that you learn as a physics PhD student at a physics summer school, obviously, to actually make this measurement. So this gap is real. It's very difficult to bridge. Okay? Just because you label something in your simulation as, I don't know, influence, doesn't mean that it relates to what is real influence in society at all. That only indicates your intention that it will be influence. Okay, so that's the first most fundamental reason why it might not be possible. All right, okay. So it's not obvious what works in physics will work for us because we're dealing with a much larger gap than they are in physics. Okay, second reason, I wish I hadn't done the animation for this. There's a very important lack of knowledge in what we're trying to model. Crucial. We have no idea what goes on in our heads, okay, as in terms of a cognitive model. There are no reliable cognitive models out there you can take off the shelf and put in your simulations to make your agents act realistically. Okay? Various different traditions have their traditional kinds of models. So in economics there's these traditions of bounded and perfect rationality, etc. They're all rubbish. They don't work. Okay? Neither are any of the cognitive models. There's a whole community that does cognitive modeling, but they're interested in little teeny questions like the timing of remembering word pairs and things like that. And even then they've got no idea whether they've got it right. Okay? So you are stuck with trying to do an agent-based model and you've no idea how to program the agents. Okay? Nor does anyone else. And in case you think this might not be important, you can try it in some of your simulations. You can try and say, let's run the simulation with this cognitive model. Let's stick another cognitive model and see if it makes any difference with the same inputs and the same outputs and roughly the same learning, like a genetic algorithm in one and a neural network in another. So that it's using the same information coming in and the same information going out. And in some models, you get totally different results. The one I've tried is sort of artificial stock market models, and it seems to amplify these little differences. Okay, it doesn't average them out, it amplifies them. So at least in some cases, it could be actually critical to your results, that you've got the right model, yet we don't know which one we should use. Okay? Lots of people will just take an off-the-shelf model from AI or machine learning or something like that and just say, okay, well, we'll use a genetic algorithm for that sort of learning or a neural network for this sort of algorithm learning. And due to this result, you might not get the right one. Okay, so we're missing a crucial part of what we want to actually simulate. Are you ready to give up yet? No? Okay. Reason 3. Social sort of mechanisms or causes or processes as we think about them are famously sort of intertwined. They're not easily separable. Okay? So in physics, you get this picture whereby you've got the main things you're trying to simulate for your atoms, and then you might say, okay, but we haven't included changes of temperature, so that adds a little bit of a change, and then maybe change in gravity, but it's a little bit of a change. And you get lots of factors, and as you get to less and less important factors, the effect on your main results diminishes. We have no idea whether this will be the case in social simulation. It might be that you add in social norms, your results completely change. Context dependency, your results completely change. Reputation, they might change again. And as you add in each factor into your social simulation, your results might completely change. It's not like in physics where the effect might diminish and you can safely ignore the rest. We have no idea where to stop and actually make it work. Okay? Yes, okay, I've said that. So, what we're doing is how you frame your social phenomena, what all you do or do not include can be completely crucial to any of your conclusions. Okay? So you really do have to think about what is and isn't relevant for what you want to study. And there are no guidelines. It might be that it's all relevant. People do surprisingly tricky things in complicated ways without thinking about it. Okay. You may need some evidence about what and what isn't should be included. Okay, so social phenomena might be extremely context dependent. That is, how we behave in a lecture theatre might be totally different from how we behave in coffee. In fact, it obviously is in many respects. Okay? So we have learnt how to behave differently in each of these different contexts. It's been trained to us. So that means you probably can't have any sort of generic model of cognition in the heads of your agents, because as they move from context to context, they may change their behaviour completely. People are known to behave very differently, for example, in situations of high risk and low risk. Okay? So market traders in a stock market, if you talk to traders, and the market's jittery, and they think, oh, the market's really jittery, they actually behave differently in a falling market as in a rising market. They don't behave the same way. Okay? So any assumptions that you've got this global model that will work across all these different contexts that people navigate from day to day, you know, you've gone from your home, from your room where you're sort of dressing yourself, to the breakfast, to walking between the two, to finding your way here, which I was obviously the worst, into the lecture. All of these things, we've got different ways of behaving. Okay, and this is a big problem for us because unlike physics, where we've got fairly general laws, the atoms don't know where they are. They don't know what context they are, or only in very limited ways. We're not consistent in this way. It might be that every single observed instance requires its own simulation model. Okay? That makes most of the projects listed by people in the introduction impossible, because they involve at least more than one social context. And social context is particularly important because social context is instituted. So over time, society has created this thing called a lecture. We've created a room for it. You all know the way to behave in a social lecture. You know what to expect. You've been taught a whole lot of rules about how a lecture works, going back, I guess, to Greeks, also who invented this way of imparting knowledge. But you know certain things aren't going to happen. This doesn't usually happen in a lecture. Okay, you all know that. Okay? So some things happen and some things don't. And there's a lot of context-dependent knowledge that you bring to bear to understand this particular situation. Okay. Reason 5. Okay, I've only got 5 reasons I'm going to tell you. Okay, this is reason 5. It might be that any simulation model that is good enough to represent what we do, for whatever your modeling purpose is, might be so complex that we can't understand it. Okay? There might be no middle ground where you have models that are a bit useful and a bit understandable. We don't know whether there's any middle ground. Okay? I like to put it in terms of the anti-anthropocentric principle, which doesn't run off the tongue, which is basically that the world is not made for our convenience as academics. You know, when people assume that the Earth was in the middle of the universe, you know, that was sort of convenient for us, or that man was a special place in biology, that sort of seemed convenient, or that, I don't know, our cognition is truly general and can do anything, that's sort of convenient. No, or that we can assume that people act as if they're economically rational. That's nice and convenient for us. It always tends to be false, okay? All these things where you assume it because it's nice, it's convenient for you as a researcher, it makes things easier for you, are almost always wrong, okay? And one of our assumptions is that any model we make will be simple, that's good enough to work, we'll be able to understand it. There's no guarantee that this is true at all, okay? And if it's not true, we can't even check if what we intended to be true for our simulation might be reflected in the thing we actually programmed. Because if we've got this really complicated model, you can't check all its bugs. Me and David implemented a really, really simple simulation back some time ago, and it took us 3 or 4 months going backwards and forwards, trying to find the mistakes and trying to find the teeny little wrinkles that made a little bit of difference in the output. And that was for a dead simple one where there was no agent cognition at all. When you have anything complicated, you've got no chance of completely checking it. And if what I say here is true, there's absolutely no chance of completely checking any of our simulations that work. So we're stuck between choosing simulations that are simple enough that we've got some chance of understanding them, and complex ones that might work, might relate to what we observe. Okay, so summarizing those 5 reasons why it might not be possible. There's a nice saying, to a man with a hammer, every screw looks like a nail, okay? Just because we've got this technique, there's a big tendency to look around and say, oh, I can hit that with it. You know, I can hit that with social simulation, I can hit that with social simulation. Just because it's what you know to do. And it takes a long time to learn new techniques. So once you've learnt it, you might as well use it, right? Okay? But it doesn't necessarily mean it's the right tool. Social simulation, agent-based simulation, individual-based simulation is just a tool. It's not magic. It has some properties which I think are particularly helpful for social phenomena. It certainly seems to be more promising than analytic sort of models. But we don't know whether it will work. As soon as we put conclusions out, and you get this particularly if you present results from a social simulation to actual sociologists or social scientists, you will find that you're open to a lot of criticism. And the more sloppily you do it, the more criticism you will get. And this will be justified criticism. Okay? And so if you present to sociologists, what you get is, but you haven't included factor X. And then you discover, oh, this particular group is socially disadvantaged and stuff like that. Some story that you hadn't included in your model. Okay? So we are very vulnerable to criticism as a technique, and as we apply it, we're seen as sort of the enemy by a lot of social science. Okay? So my faculty thinks of my centre, my research centre, as a, quote, nest of evil positivists. I've asked this, I've checked it with some of the faculty, and they'd say, yes, that's about right. I don't know where they got the evil from, but anyway. So we've got a lot of criticism to deal with, and a lot of convincing of many of our colleagues that what we do actually works, makes sense. Okay. Any queries, questions at this point? Yes?
Do you think there's a danger here that you're kind of, your criticism applies to your presentation in the sense that you're talking about modelling, agent-based modelling in general?
Yep.
And saying, in general we can't do this, can't do that. Surely the way out of these problems you identify is you talk about, you contextualise what you're talking about.
Yes. Thank you, I'll pay you later. Okay. Okay, so now I'm going to look at this, why, even though it's really difficult, it might seem easier than it is. Okay. I'm starting to see the depth of my pessimism here, I hope. The first is an effect called theoretical spectacles, pointed out by Thomas Kuhn in his famous book. And what he pointed out is when you adopt a theory, you believe a theory, you tend to see the world through that theory. So you tend to notice the things that agree with it, and you tend not to notice the things that disagree with it. So his famous example is the geologist looking at tectonic plates and whether they moved. Okay, I can actually remember my geography teacher saying, you see a connection between the coast of Africa and Europe and the coast of America seems to fit together. That's total coincidence. He told me this, okay? This is my school teacher. And a lot of geologists thought that. The idea that these things moved was just anathema. And they just ignored lots of evidence, including the coastlines, for ages, okay? Because of this effect. And the fact is we can't avoid seeing the world through some sort of theories, through some sort of assumptions. You can't avoid it, okay? Your ideas about how the world are intimately bound up with our perceptions. Okay? Now, with agent-based modelling, this effect is particularly strong. Okay? When you've played with your model that you're building up, your fun little model that you're building up for a week, you really do see the world through this model. I've experienced that. I mean, the world really does look like my model after I've played with it about a week. Okay? Partly because it's so amenable to this interpretation. You've got these dots moving around, they're doing things with labels on that you recognise, and you can interpret it. It's easy to interpret, not like a horrible statistical model. It's this thing that's a relationship with factors. You can see the movements, you can almost put in nice little stories in your mind about what's happening, okay? And the fact that you're interacting, that it's very interactive. Unlike a statistical model, you have your hypothesis, you do your test, you get your result. It's pretty dry. With a simulation model, you go through this iteration of playing with the model, thinking of the results, trying it. You get emotionally involved with your model because you're playing with it. Okay, it's a toy. And that involves you more and makes this effect doubly strong. Okay, so a huge danger of social simulation is that it's convincing far beyond it should be, including to yourself. Okay, so that's one reason why, although it's very difficult, it might seem easier. The second one, okay, is about the use of analogies. People are very good at naturally applying analogies to different areas. So if I said a little story like, and then Nigel Gilbert came into the room and the shit really hit the fan, okay? As he just has come in, okay? You can all imagine what that might mean in terms of a story. You can fill in what it might mean by this analogy, okay? I was in a project which modelled water ages ago, and they used to say when the anthropogenic nutrient hits the turbine, but that's a different version of it, okay? So, humans are very good. In fact, some thinkers have claimed that this is the very basis of thought, that all our thought is analogical, which may be the case, I don't know. Okay? But the fact is that we're very good at applying an analogy to a new situation. So if I apply the same idea to a different situation, we all went to dinner and then the shit really hit the fan. Okay? You immediately connect different references to my story to the new situation on the fly without having to really worry about it. Okay? So that's one of the characteristics of an analogy. Every time you use the analogy for the thing you're thinking about, there are different mappings from the sort of story, the analogy, to what it's referring to each time. We discovered all this phone hacking, then the shit really hit the fan. You can immediately see what that means in that situation. This is quite different from the applications where what your model refers to is fixed and well defined. Okay? So when we're applying a model of planetary motion, how you apply that to the measurements of where planets are is fixed. Been decided. There are lots of ways of doing it, but there's a methodology for doing it and what it refers to. The model of planetary motion is not an analogy, it actually refers far more directly to the observations than that. Because each time you apply it to that, there's one way of doing it. There's not 26 ways like an analogy. There's not lots of different ways of like interpreting a novel. So if you all read a novel, you'll interpret it in different ways. It'll be richly meaningful to you, maybe, but it'll all have different meanings for each of you. Now, the point about this is simulation models are really good analogies. They're really powerful as ways of thinking about your phenomenon that you're dealing with. They give you rich insights into what you're doing. Okay, they improve your intuition, but this is personal knowledge. It's very rarely public, communicable knowledge that's useful to other people, maybe really useful to you. In fact, one of the main results of doing a PhD is you develop this rich understanding as a result of going through and doing a PhD. But your conceptual framework, which is what usually PhD students, including me, I may add, including me, want to tell the world about, is not what's useful to everyone else, okay? Because your way of understanding things is more particular to you. Now, so it seems that, so what seems to happen is that you can imagine your model applying to this situation very vividly, because you can sort of construct on the fly how that might relate. But that's very different from something that more directly relates to what you're observing. It has more solidity that's worth communicating to your peers. Okay, people disagree with my view on analogical thinking, so if you ask other people, they will give you a different view. Okay. Sheer wishful thinking. Okay, this has got to be number one. You've learnt how to do simulation modeling. You want it to work. Therefore, you find ways to convince yourself that it does work. Okay. We can imagine how it works. We might fool ourselves. It's a lot of work. You know, you do your model and it turns out to be wrong. What do? Do you junk your model? It's taking you 2 years to make. Do you just throw it away and start again? Well, you should, but most of us won't, including me, okay? I throw away quite a lot of models. My peers tell me that's to do with the quality of my models rather than anything else, but... Okay, so it's a lot of work. Final sort of way is that people conflate and confuse why they're making the model. Okay, so for example, I've tried to indicate the difference between an analogical application of a model and something that has a more direct relationship with what we observe. Other confusions append, and I'm sure a lot of the other people who are talking will point some of these out. So a key one is the confusion between explanation and prediction. Okay, this is very widespread in economic models. So if you're trying to explain some data, you might have some in-sample and some out-sample data. And you condition your model on the in-sample data and you see whether it tracks the out-sample data. And what you then have is an explanation of the connection between the in-sample and out-sample data in terms of your model. It is not a prediction. A prediction is something that you don't know about. Okay? A prediction has to be unknown data. This is not a prediction. If you had something in economics that predicted, everyone would say, okay, you get the Nobel Prize, no question. But they don't. So in a lot of economic papers, there's this fudge of explanation and prediction. They pretend it's prediction, but they don't predict unknown data. They predict known data. I'm very good at predicting known data. Another confusion is that a purely conceptual explanation is confused with what actually happens. So you've tried to look at the evolution of cooperation, and you found these very interesting stories and ideas of how things might happen, and then you say, okay, now we understand what did happen. So, etc., etc. There are a number of these confusions. So, in a sense, I'm trying to eat away at your optimism here. Told you some reasons why it might be really difficult. Told you some reasons why you might be fooling yourselves, and I've done this, okay, I've done this. I've fooled myself in all of these possible ways. Okay. So now I'm going to talk a bit about the relationship between models and what is modelled. Now, there's a traditional picture of this, which goes back to at least the 50s. Mary Hess, I think, was the first to use this picture that I found in the philosophical literature. So you have some system, and you have some aspects of it that are known and some aspects that are unknown. And really what you want to know is what comes out here when you stick things that you know in there, this is the thing you're observing, and what you do is you build a set of relationships to a model. So you encode what you know, and they come as the input to your model, and your model produces some output, or the results, and you interpret it back to the system. And so you can infer some things about what you're observing using your simulation model. Okay. So it's a very traditional picture of what's happening here. Now, this model can be anything. It can be mathematics or just a story or a simulation model. For the purpose of this discussion, it doesn't actually matter. Now, what's important about this is to use a model, you need 3 stages. You need to interpret it in terms of your model. You need to be able to work out something with your model and then interpret it back to what you're talking about. And the use of a model is only as strong as the whole chain of the 3 steps put together. If you have really good understanding of your model, but these bits are weak, then you haven't got a very good chain. If you've got really good relationships here, but you don't really understand your model, it's not very good. And those might actually, I've already anticipated my next 2 slides here. So with a descriptive model, this sort of model I sort of like, you have a really close connection, or you try and make as close connection between what you observe, the evidence, and your model as possible. Okay? So you try and glue your model, you look at what happens, and you try and make your model the same way. If your experts or your stakeholders tell you that this and this and this and this and this are all important, you try and put all those into your model. Okay? A descriptive model is a nice polite term. A kitchen sink model is another one, i.e. you put everything in it, including the kitchen sink. So, this is as strong as relevant. So things in the model, you know that this bit refers to that observation and this bit refers to that observation. So you've got a good idea what your model means. There are no sort of parameters in that will be conditioned on data. You don't know what they mean, but they're sort of conditioned on data. There's nothing like that. Okay? However, what usually happens when you're modeling anything social is that your model gets so complex you don't really understand it. Okay? You've got some idea of what's happening, you think. But if you change this parameter, you don't know whether the whole thing would change. And usually there's so many different parameters, you can't possibly explore the whole space. Okay? So here we've got relatively strong links with what you observe, but a relatively weak step here, because you can't rigorously check your model. The other extreme, oops, oh yes, so not only you're connecting the n bits, the input and the output, you're often trying to make it actually mirror in some ways the details, the processes that are happening inside that. It's the opposite of a black box model. Okay. The opposite of that is an abstract model, where you have some fairly simple model that relates very distantly to what you're observing. Okay? This is very strong on rigor because you can exhaustively explore this model. It's probably simple enough that you can do some analytical approximations of it and check that you're getting the right answers. You can find a coherent story about why the model is acting as it is. There can be lots of discussion about this. If you want to get cited a lot, this is a good sort of paper to write. If you write a nice simple simulation project, no one can resist trying variants of your model, okay? And when they try variants of your model, they think, oh, that's an interesting variable, I'll write a paper about it. And you get cited, okay? So if you want to get lots of cites, this is a good way to go. Okay, it's a very social approach to our object area. But the relationship between what's being observed is relatively weak. So for example, in a prisoner's dilemmas model, which is one of these kinds of models, okay, it is actually very difficult to find any situations where it actually does relate to a prisoner's dilemma situation. Okay, people stick it in because it's nice and simple. You don't want to muck around putting all this environment and all those bits, how people interacting. You just stick in a prisoner's dilemma, stuff like that. Okay, but it's actually very tendential that there'll be any relationship, especially if you're looking for relationships of the actual model outcomes and any measurements on your object system. What actually usually happens in this circumstance is this, is that what actually has happened is you have a model of your ideas. So in the prisoner's dilemma, there are a set of ideas about how people might interact, and you have a model of those ideas. And what actually refers to your thing that's being observed is via an analogy. So it's a two-step process. You have an analogy. Your ideas help you understand what you're observing in a rich, normal human way. And then you have a model of your ideas to try and understand the implications of your ideas. So this is a very common pattern in social simulation. But you can see it sort of fudges the issue, doesn't it? What is the relationship between your model and what you're observing? It's a bit indirect. Because the ideas, as they apply to this, might not be the same ideas that are actually instantiated in your model. The way these ideas apply to what you're observing is a rich human construct. This is a different construct altogether. You've got to be absolutely certain that the same ideas are in your model as linked to your object system. And even then, how these relate is a bit fuzzy. So it seems a very convincing way to go, but how do you still then know that you've done this bridge, this gap, that what you're observing is reflected in your model? Still very hard, okay? But it's a very common pattern. Now, because I'm pretty pessimistic, I think there's going to be a lot of work we'll all have to do before we get to any really good models. I don't mind this kind of thing as long as people are honest about it. And they say that in the paper. So there's usually a bit at the start of papers you read where it's the motivation, right? You know, issues of trust are really important, blah, 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 refer to him and refer to them and refer to them at the start of the paper. And then you get to the model. There's a sudden jump, okay, to this quite artificial model which you get into. And you're left to make the connection yourself. In good papers, the conclusion are very cautious. They'll say, oh, maybe this suggests this hypothesis or that hypothesis. Bad papers, you'll say, we now understand how trust works, and therefore there's following policy recommendations. And believe me, there are papers like that, okay? Which is obviously not justified by such a structure. It may suggest hypothesis. That's a good use. It may suggest good questions. That's a good use. Okay? It won't tell you how this bit works. To summarize this bit. If you're not satisfied with yet another way of thinking about stuff, it's like WYSIWYG, but it's Yawatas, okay? Yet another way of thinking about stuff. Then modeling is easy. If you're satisfied with just analogies, then we can be pretty slapdash about it. Because people are good at using analogies. So if it's fun and it's sort of interesting, you can produce a model and people will use it creatively as an analogy. But then you've got no particular reason why you're using a simulation model. Why not tell a good story if you want a good analogy? Why not use 100 other ways of producing a good analogy? And if we're doing this, we're only using it analogically, we can only make extremely weak claims about our results. We can't advise anyone. We can't really suggest anything apart from maybe hypotheses. We can't answer questions. We can't test questions. We can't do anything like that. Okay? But if we're not going to do that, if we're not just going to do analogies, but we're trying to look for something more than that, we're more ambitious, then we're stuck because we need both rigor, that was the case with a simple model, we understand the model, and relevance for our social simulation to work. Now, you tend to get one or the other, and never both. Actually, I tend to think you're not going to get them in a single model. And what you'll have to be stuck with is a chain of models. That's my personal view. Okay? But really, for good science in a final way, you need both rigor and relevance. You can't just do with one or the other. How am I doing for time? Okay, I'm doing fine. Right. Now, one of those points was the conflation of different purposes for simulation. There are lots of reasons why you might make a simulation. Okay? Number one, to entertain. Most of my simulations are initially conceived because I find them fun. Okay? They entertain me. Maybe you're using them to illustrate a process. It's very difficult to sort of understand some process, how it is and how it all interrelates, and you want to show people how it could come about. So you might use it as an illustration of an idea. You might use it to design an artificial simulation system. Okay? So you're designing a new P2P system. How do you do that? Well, let's put a simulation and try different policies and see what happens. Okay? To give you an idea of how the system might work and what's the best way of designing it. There are people who use participatory simulation who want to mostly do this. They want to mediate between people. So you might go into a village, you might play games on a board, and everyone's talking about where the water allocation should be, and you play this with the people. You go back home during the night, and you program during the night, and then you present the next version to them in the morning. And you do that all week, okay, until you're wasted, but happy. Okay? So there the aim is not to represent anything, it's just to mediate between people. Okay? It might be very effective at that. I've talked a lot about Friday way of thinking about stuff. I guess it's a sign of age when someone comes up to you and says, there's this new paradigm, and your heart sinks. Last thing you need is a new paradigm, okay? What you need is something that will work a bit, okay? New paradigms, new conceptual frameworks, thinking about things, they've got to be really, really good to be worth it, to be honest. I know, I was the same. I was a PhD student. I had this new paradigm. I wanted, to do that. But, okay. So maybe I'm just getting old and bitter. Do you think of that? Maybe? Perhaps. Okay. Okay, but there's these 4 different ones I'm going to talk about a bit more detail here, maybe give some examples of. To critique or clarify some ideas, to predict, to explain, and to analyze a mechanism. Okay, so I'm not really going to show you examples of those. Look at those there. Yes?
What about learning?
Oh, yes, it's not exhaustiveness. There's lots of other things. Lots of things I haven't listed.
Because my conclusion of your previous part of this presentation is that you propose that simulation is better to learning than to apply.
I hope that it is possible, but we've got a lot of learning to do, so yes, in that sense. So it depends on what stage you're at. But of course, I'm a pessimist, so I would say that. Okay? Well, I'm not generally a pessimist, just with regard to what I do. Okay, now, these are purposes for simulation. They will relate to your research question. Edmund, who's going to do the next lecture, will talk more about your choosing a research question. Okay? Obviously, if you've got a research question, it might involve one of these things. Okay, I'm talking at a fairly abstract level here. Now, that is different from ways of judging models. Now, when we make a simulation model, we want all of these things and more. Okay? We want it to be designed well. We want it to have a lack of error in our results. We want to be able to understand it. We want it to be able to apply it in more than one case, etc., etc., etc. Okay? Plausibility. How the processes in your model works are roughly how things seem to work in what you observe. You're going to have your simulation's going to finish before you're 50. Okay, in my case, older. These sort of things you want, but these are different things than your purpose for building a model. Okay? These are what you're trying to do with the model. These are ways of judging your model when you get it. Now, people confuse these two often. They say, okay, I'm doing this model and I want it to be simple, therefore I'll do that. These are how you judge what you get and maybe how you choose which tool you're going to use. What's important is your purpose for simulation. There are obviously lots of trade-offs between these ways of judging your model. Sometimes I like to put a picture of here just to illustrate the trade-offs. Obviously this is a very simplistic picture and the trade-offs might be very complicated. So if you like, you know, what do we have? Statistics might be along this line here. Tend to be quite simple models and you've got to match the results. Or philosophy. Philosophy, you like generality. You don't like simplicity. And there must be no counterexample. So maybe philosophy is along this one. Getting them all four at once is really difficult. Okay? Usually any particular technique does two of these well, and then you're struggling for a third. You certainly don't get all four. But these are just some of the trade-offs you're trying to make in how you're getting to your modelling purpose. Okay? You do have to make complicated trade-offs and things between things in any field of study. But the ultimate gain is your aim is your research question, these reasons for modelling. Okay, so that's what I've said in this slide, really. So there's a big difference between your modelling goal and the criteria for judging them. These different goals and methods might imply different trade-offs, but the choice of your methods is separate from your modelling goal, okay? So try and think what you're doing and take on board the trade-offs you're going to be stuck with trying to do that. And that might say, okay, we'll use this tool for some of your research and this tool for the rest of the research. And this bit to help this bit, okay? That's a much more pragmatic sort of mixture, and the goals for your research are far more fixed by, well, often sometimes the field in which you're in. What are the important questions? Okay, so I'm going to briefly now go into 4 examples very quickly to try and illustrate some of these points before I finish. So, the famous one, you can't be a social simulation summer school unless you see the Schelling model. Okay, so here it is. Is there anyone here who doesn't know the Schelling model? Good, okay, right. So, this was a very simple but groundbreaking simulation. Its purpose was conceptual clarification. If you read his papers and his book, what his central reason for this was, as I interpret it anyway, is that the macro scale segregation we observe doesn't have to be caused by a strong preference on the social actors. So people didn't have to be racially prejudiced to a big degree to get the segregation occurring. It can be a very small degree of intolerance. Okay? And when you get a small degree of intolerance, segregation can still occur. Okay? So in a sense, this whole thing was a counterexample to the assumption that if you get the macro effect, it must be mirrored in the micro effect. Okay? It doesn't directly apply to anything observed social processes. Okay, it's very difficult to get this model to link to any data. There are people who have tried with some cities, sort of Schelling-like models, but they don't do very well, in my opinion. It doesn't predict much, and only later works looked at analysing and generalising the mechanism for that. So it had a very limited intention on behalf of the author, and yet it's then used by other people in lots of other ways. Okay, so you get this change of context from why it was invented to how it's used, which isn't necessarily, doesn't necessarily preserve the validity of the simulation when you're trying to use it for a completely different purpose. The second example is each general election night, BBC and ITV have this election model which tries to predict the results. Okay? So, for some reason the BBC is absolutely obsessed with telling you what is just about to occur, rather than letting you wait and discover it. Okay? So you listen to the Today programme, and they will speculate about a report that's going to appear at midday. And why don't you just wait 4 hours, okay? I don't know, but they do, okay? And so BBC and ITV jointly commission this model done by John Curtis, David Firth, and then they're the main lead researchers. Then there's a host of others that put input to this model to try and predict the result of the election, the general election. What does this model do? Well, they have a separate statistical bit for each constituency. So they try and condition the swings, looking at the history of swings in that constituency, separately for each constituency given the data. Because they're in a data-rich arena. There's lots of data about who voted for what in all these elections. So each constituency is modelled in a swing between Liberal Democrats, Labour and Conservative. And then when you see so this picture here, is each line with a green dot, tadpole. Each of these tadpoles is a constituency, okay? The green dot was the result of the vote shares in the 2005 election, and the tail was where it was in 2001. So you can see the movement of shares in all of these different constituencies. And there was a shift away from Labour. You can see lots of tails down this end towards Labour coming back the other way. So it's a sort of what might be called a micro-statistical or micro-simulation model. There's a different set of equations and parameters for each constituency, which are then conditioned on past data. And then you look at once you've got about a lot of the data in, you can make a prediction of how many seats they're going to get by the end of the night, by the next morning. Okay, so its purpose is to predict. It does predict. But it requires to predict, well, about 30% of the real results in before you get the prediction for the next day. So it predicts the rest, the other 70%. Not individual results, but how many seats each of the parties have. So there is a social simulation which predicts, but it uses masses of data, huge amounts of real data, because, I mean, in a general election, how many people vote? So that's your data. It's like having a survey of half the population. Okay? And then it only predicts about 8 hours forwards. Okay. Third example, opinion dynamics models. Now, what the purpose of this is, it's a very abstract model. It's looking at mechanisms. Each person is modelled by their opinion, which is usually on a scale of 0 to 1, and its level of uncertainty, whether you're really uncertain about your opinion or very certain about it. And the basic idea is if you're randomly paired, and if the person is within, their opinion is within your uncertainty bound around your opinion, then you adapt both your opinion and your uncertainty a bit to match theirs. That's the whole idea of the model. Okay? So each of these opinions. Now what happens is they then start the simulation. So in this simulation you have 5% of extremists here and here, each of which have very low, extremists here and here, have very low certainties. They're very certain about their opinions, and a whole lot of moderates who are very uncertain about their opinions, and you run it. Lo and behold, what happens? Everyone is attracted to the extremists, either one way or the other way. Okay? So, a few certain extremists can polarize the opinions of the moderates. Now, there are several parameters of this model, and you get different regimes and different sort of behaviors depending on these parameters. What do, the authors? Well, they're interested in understanding the mechanism. So they do a very thorough analysis. So this is the uncertainty of the moderates, and this is the percentage of extremists. So, okay. And they map out the results of all of the changing parameters. They do lots of analytical generalizations and approximations. So they have various theories of this in analytical maths, which they check against their simulations. They try lots of variants to see whether it makes a difference. So they do a lot of work just to understand this one very simple mechanism. Their aim is a sort of pseudo-mathematics. They want to understand this mechanism. They're not really saying this is what happens in the real world. They were motivated by what they saw in the real world, but they want to understand this mechanism. Okay, so this is another example, like the Schelling model, of a relatively simple model, although it turns out not to be so simple to analyze. Okay, but it's not something with a direct connection with the real world. Had a motivation from there, but it's not necessarily describing anything we observe. It could be, might well be, but we don't know when and where it does. Okay. So the fourth example is one from our own centre, quite an old one, was a model of social influence and water demand, which was done in conjunction with the water companies in this country. And part of it was done in the original project called an EU project called the Firma project, and part of it was done as a consultancy for DEFRA, one of the government departments. And this is a typical clash of policy advisors and academics. What they wanted to know was, really, all these water companies, was how few reservoirs can I build and not be blamed when climate change increases, okay? So because if you tell me a number, you've got to build 3, then if there turns out to be water shortages, it's not our fault. And of course you don't want to build reservoirs because it's all your cost, hugely costly to build a reservoir. Almost all the cost of supplying water is the cost of building reservoirs. And so all of our niceties and complexities that we introduced, they weren't interested in at all, okay? They didn't care. Whatever number we gave to them, as long as it wasn't too many reservoirs, they would be happy with. Right? Okay, so, but we tried to build a quite detailed descriptive model, and our main aim was to try and explain the deviations from the statistical models, and the most of this government project was statistical models. We were just stuck on the side of water demand, how it differed from that. So it was a quite complex model. We had households who were in a sort of social network looking at each other. They all had different devices like washing machines, showers, taps, toilets, etc., of which we had statistical information about how often they were used and the volume of all of these devices. Okay. There was a policy agent who was trying to advise them when to use less water, which was fed in with actual climatological data based on a model of groundwater, okay, which the sort of water companies tend to use. And then it results in this aggregate demand. So there's a very complex social process happening between the households, which I won't fully describe because we want to finish soon. So there were different kinds of households. Those which were amenable to advice by government or the local water company. Those who tended to look at their neighbours, and those who tend to be just make their own decisions. This was all households were a mixture of these three, but you know I'm just simplifying here a little bit for presentational purposes. And you can see who is mostly. This is the prime influence out of each one. So this one influenced that one and that one more than others, etc. So you can see the pattern here coming out in a particular thing. And we got output from this. So this is the relative demand for water from 73 to 97. Each of these lines is the amount of water for a different run of the same simulation model. There were two big droughts, one there you can see, and one there, where people were trying to advise to use less water. And these black lines were the introduction of, I think, of power showers and water-saving washing machines. So they were a technological change that changed in what people could use. Of course, what you see is every time you run it, you get a different answer. okay, for a start. Secondly, you see, although there's some commonality in behaviour, the effect of a sudden shock can be very different. So, for example, this one started the drought using not much water, and actually after the drought used a lot more water, while some used a lot less water after the drought. And that was due to, in this model, the lock-in between people copying other people's usage of water in the area. Okay, so you see whether people, your neighbours, are using the hose illegally on their garden, then you might copy them, or you think it might be all right, etc. Okay, so there's a big deviation between different districts, even given the same conditions, which is what was found in the actual data. When they measure the water demand in different districts for the same conditions, they find very different patterns. It's always clustered volatility, sort of spikes coming up in big spikes, but they're different patterns for each area, even for the same climate and advice. Okay, so this model provided an explanation of why that might be so. It's only a candidate explanation. In a sense, why there might be a deviation from these nice, clean statistical models, which tend to be fairly uniform. Okay, so by including that, we saw some patterns that seem to be similar to what we observed. It was possible that processes of mutual social influence could result in differing patterns of consumption, and thus it was a candidate explanation for these various characteristics we saw of the demand. But it still doesn't tell us that that's what happens. It just tells us, look, this is a transparent model. You can see the individual steps, trace through it, see what's happening. It might be an explanation of what's happening. The real answer is then you have to go out and check this. Okay. Conclusions. Let's finish conclusions here. If social simulation is not impossible, okay, then it is at least very hard. Okay? It's not easy to do. We've got a big task ahead of us. There are lots of different reasons for simulating. Each of these entail a different compromise in how you're approached and how it might be judged. So I hope I've just stimulated you to think a little bit more about what you're doing and why, and to approach this at least a bit cautiously. Try and think what you've said. In some sense, the area of social simulation is maturing. Okay? Everyone piles in at the start and it's great fun, and you just do a model and you play with it, it's all exciting, and you've got these results, and they seem to really tell you something. You write your papers and stuff like that. But in a sense, the whole field is trying to go a little bit further than that, try and tighten things up a bit, and actually try and do some better social simulation of what's really out there. I sometimes feel that I'm always a killjoy. I'm always telling people not to have so much fun in social simulation, but to do it better. Whether I ever reach my own criteria, I would say I fail in lots of different ways in my models. I'm trying to do what I'm saying, but I certainly haven't achieved it yet. Okay? There are people with very different views about this. Okay? So I'm one extreme who will say that sort of somewhat compromises are a bit helpful. They help us a bit. I'm a skeptic, okay? So I always see the difficulties, maybe. But I think it's a project that's worth pursuing. It's just not certain that we're going to succeed. There you go. There's a good bit in Lord of the Rings where Gimli the dwarf says, you know, 2,000 people against you, 3 of us against them, no chance of success. What are we waiting for? Well, that's the sort of message that we end this talk. Thank you very much.